All right. There's some terms in here. Can you guys state off some of the terms in that first section or first page? First about 3 pages. What are some things you see? Go ahead. Aqueous solution. You guys know what that is?
It's like, okay, it has to be like solid and like liquid and that stuff.
Right.
Oh my God.
So, right. So AQ, you have water, and you have some other things in there. So when it's a solution, it's just a mixture. So aqueous, it means that that it's a combination of 2 things, 2 or more things, and usually it's something dissolved in water. So we're going to look at 2 words associated with aqueous solutions here in a little bit. There's another thing down at the bottom. What's that referring to? What's the term associated with at the bottom? Okay, so polar molecule. So I'm going to show you what a polar molecule kind of looks like. You don't have to draw this out, okay? So a polar molecule is like this one right up here. This would be what you look like when you would draw a model of something that's polar. And polar means that on opposite sides, they have opposite charges. So if something is a polarity, it means it's not neutral, but it's offset. One side is going to be slightly negative. Sometimes it's strongly negative, and sometimes it's weak negative. But there is some difference in charges on both sides. So water would be an example of something that's polar. So these are all examples, even though I didn't put pluses and minuses on these. Oxygen takes on a negative, and there's a reason for that, and we haven't got to that yet, and we will eventually. But just realize that some molecules are polar and some molecules are nonpolar. Nonpolar would be, for example, this would be a nonpolar molecule, and I'm not going to explain why right now, but if we have carbon bonded to 4 hydrogens, because of the makeup, this would be nonpolar. So I'm not seeing any pluses or minuses that are drawn out. And most of the time, water is not going to have any pluses and minuses, but there are some things that are called polar, and there are some things that are called nonpolar. So this would be nonpolar. Right, and we haven't got to the point where we really went through in detail on that. Water is polar, so this is an example of polar. And in this over here is an example of something that's ionic. In a way, it's polar too, because you see the pluses and minuses. So it is polar, but it is an extreme polar, and we don't say it's a molecule, but it is extreme difference in charges with the sodium and the chlorine. So that's kind of how we get into polar molecule. Will just be covalently hooked together. This is over here. This is ionic, and the ratio is 1 to 1. So this is NaCl. All right. So this over here is NaCl. And so that's ionic. Okay. So turn over the page, next page, and you have some other things. I'm going to show you hydration and solubility. So down below on page 118, you have some drawings that I'm going to kind of attempt to use here. So if something is hydrated, what does that mean? What do you think? If something's hydrated? Yep, water's added. Water's pulled in. Water's added, and it's soaking in. So that's hydrated. And so a process of this NaCl dissolving, okay, or dissociating. So a lot of times in chemistry you'll hear something that dissociates. Dissociates means breaks apart, separates apart. I'm dissociating myself from you guys. Okay, I'm breaking away from you guys. I'm not associating with you anymore. Okay, and so that's what dissociation means. So what happens is this water molecule here moves over here, sees NaCl, and there's a portion of this water molecule that's attracted to a portion of this compound. So what portion of the water here is attracted to what portion of this sodium chloride structure? So what's the oxygen, the red atom, which is the oxygen, what's it attracted to? Na. So it comes over and it attracts itself to Na. All right? And so this part of the water molecule will attract itself on to the Na because it's going to be negative. All right? And the positive side definitely stays away. And what it does is it attaches itself and then it pulls away. So it'll come off, pulls away that sodium out of that substance. And you get what would be pulling away the Na+. So it pulls it away. It keeps doing that until it gets to the point of saturation. So we'll hear this term called saturated. Maybe not in this chapter, but a saturated solution is where it can't pull any more out. It's done. It can't pull any more out. So then that piece is gone, okay? Taken away. And so is this taken away, and it leaves behind the chlorine. So then what's attracted to the chlorine? So is there any part of this water molecule that's attracted to the chlorine? It'd be the hydrogen, right? So then it comes over and it hooks on to the hydrogens hook on to it. And it will pull away. And then when it pulls away, then what we'll have is we'll have that that chlorine. It's a little face there. So it pulls that away, and so then it disappears from over here. And so it just keeps on pulling away, and it becomes dissociated. So it breaks apart, becomes dissociated. Down below on page 118, they do an excellent job of showing that. And it shows it just surrounding, each of the ions are surrounded by a bunch of water molecules, not just one, but a bunch of them. And so they become superhydrated at that point. So we say that the ionic substance is soluble. So there's a solubility associated with that. Any questions you guys have with that? Okay, so the next part, I'm going to show a little demonstration for this here a little bit later. So if you would turn, page 119. Now, going back to this, we've already looked at some terms like hydrated, aqueous solution, soluble, or solubility. We looked at polar molecule. So now we'll take a look at some other ones. So in a solution you have two things. In a solution you have a solvent and a solute. You have a solvent. That's the stuff that would be like water. It's pulling away the different parts of the other substance in dissociating it. It's causing the dissociation to take place. The solute is the substance that is being broken apart or being taken apart. So When we say dissociate, we mean it's being broken apart. So that's what the solute is doing. I already showed you the example with the water and sodium chloride. And it's because water is polar. Now, sodium chloride can't break apart unless it's a polar solvent. If it's a nonpolar solvent, it won't break apart. Because there's nothing on a nonpolar solvent that can be used to break it apart. All right? So, for example, in here, if this came over here to try to attach itself to either plus or negative ions, there's nothing to attach. This is all neutral. The CH4 is all neutral. So when it comes over here, it's just going to stay on the outside. And this is all going to stay together. It's going to stay on the outside. And we're going to say that NaCl is insoluble when we have something that's nonpolar. There's nothing to pull it apart. There's nothing to track those sodium and chlorine ions apart. So we would say that that is a situation where we don't have a solution that will form. And so it's nonpolar. It won't break it apart. Okay. It's important to have those basic understandings of how solutions are formed. And so we'll get into some more detail about, well, what does nonpolar, what will nonpolar mix with? And we'll talk about that here later. Okay. So I'm going to do a setup here, and we're going to go ahead and take a look at this thing called electrolytes and non-electrolytes. So if you want to write down those notes, I got a little demonstration that I'll set up. So up on the board, you have three things that can make a strong electrolyte. Well, the one that we looked at was a highly soluble salt. That's the one we looked at right in here. Okay, so highly soluble, what does that mean? It just dissolves. Okay, that's all it does. It just dissolves. It's a highly soluble salt. Okay, we can also take an acid. So this is regular water again. And we can test it. Make sure it's water. I'm not tricking you. Okay. Now let's go ahead, put a little acid in there. Hydrochloric. See it smoking? Really, really strong stuff. So we'll put a little bit in there. Okay, that's the strongest I have. Now if you notice, I'm diluting it and I'm changing the concentration because I'm adding water, so it's not as strong. And then most of the time in that form that you have, that's what I give it to you. So according to that, HCl would be a strong acid if it would conduct electricity. It does. Okay, so on the board it says strong acids. You guys will have to memorize the 6 strong acids. They are listed for you. And they're easy to remember. The first 3 are easy to remember because they're all, except for HF, they're all in the halogens. And then you have your HNO3, H2SO4. That's what that is. If you guys didn't write that down, it's H2SO4. And HClO4. Okay? Strong bases do the same thing. I'm not going to show you a strong base because I would put the strong base in there and the same thing would happen. Okay? Make sense? Those are the 3 things. What does it mean by dissociate 100%? You're saying, well, what does that mean when it means dissociating 100%? It means it breaks apart. All of it breaks apart. So, for example, the one that I did, which would be CuCl2, when it dissociates, it breaks apart into Cu plus 2 chlorines, not Cl2. Cl2 would be a gas. So it breaks apart 2 to 1. And so this is 100% it breaks apart. None of the CuCl2 solid is left over. It's in an aqueous form. Okay, it's in an aqueous form at that point. Okay? So it breaks apart fully. HCl was another one I did. I had HCl, and then it'll break apart in H plus Cl minus, and it'll be aqueous. And it breaks apart 100%. So that's what that means. Breaks apart 100%. Now let's take a look at weak electrolytes. All right, along with that. So that's the next thing I'll give you, weak electrolytes. And then we'll take a look at those to see what they'll do. So here's the weak electrolytes. They're weak acids and weak bases. And I give you an example of acetic acid here. So right here, this is acetic acid, guys. See, that's acetic acid. That breaks apart about 2 out of every 100 actually breaks apart. So that means if I have, let's say, and that's just a rough estimate, if I have 100 of this to start out with, 100 of these, and I take and start to break it apart, I'll end up with 98 of these and 2 hydrogens and 2 acetates. So I start out with 100, and at the end, after I pour it in the water, I'll have 98 of these. And I'll just have 2 ions of hydrogen and acetate, about. It has what's called about a 1.8 percentage dissociation. This means about out of 100, 2 will come off. Okay? So, I'll dump this again, get some water. Show you that it's not conducting. Oh, it is conducting. Must have left some in there. Doesn't take much. If you don't rinse it out real good, that's why you guys got to rinse your stuff out real good. Because if you don't, stuff's left behind and it contaminates your experiment. Try this again. Try it again. Alright. Got to put my... This is a homemade device. I've got some other ones that are factory, but they don't work near as good. Alright, let's try. Okay. So, I'm going to pour a little bit of this in there. About the same as what I did the other. This is nasty stuff too. Even though it's called a weak electrolyte, it's still strong. What that means is it's still got a lot of those molecules in there. So what would you think what would the light bulb do? What do you think? Let's go. Pretty dim, right? There we go. See how dim it is? Now, this stuff is actually more concentrated than this stuff. So the acetic acid is 17.4 molarity, and this is 12 molarity. So actually it's even stronger, an acid, and you don't want to mess with it, but it breaks apart, very, very small number actually break apart. Okay? So because of that, we say it's a weak electrolyte. Weak bases do the same thing. So, like NH3. NH3 would be... NH3 is ammonia, and that would be a weak base. So NH3 is a weak base. Weak acid would be all other acids that have H's out in front other than those 6 I gave you. So it'd be HF, this H, C2H3O2, that's weak. It's really important that you guys know that those are weak and they don't break apart. And that these are strong and these break apart every bit of it. So if I started out with 100 of this, then at the end I'd have 0 of this and 100 of each one of these. Okay? Because it breaks apart 100%. And that's what conducts the electricity. Okay? So you guys do not have to take notes on this, but I always like giving them visual. So we put the MX in there. What do you think it's going to look like after we put the MX in there? So it's just so what do you think is going to look like in here? All of them broken apart.
Yeah.
So M's equal amounts of both. Got equal amounts of both. So now I go weak electrolyte and I put the MX in there. It's going to look like this. See, that's not breaking apart. But after so many of these that we see, we might see one X minus and one M plus. All right, so that would be a weak electrolyte. And a non-electrolyte would be all MX. There's no ions. You have to have ions present. If you don't have very many ions present, it's a weak electrolyte. If you have 0 ions present, it's a non-electrolyte. So some of you are probably asking, well, what constitutes a non-electrolyte? Okay, a lot of molecular substances, other than the weak acids that we have. So molecular substances, like the sugar. So that would be like sugar. Carbohydrates that are soluble. Carbon dioxide. Now, better be careful with that because it can form a weak acid. Yeah, so. All right. Okay, so you guys have a little bit better understanding. What I just did for you is on page 120, 121, 123 talks about weak electrolyte. They have ethanol listed there on that. So the last thing we're going to talk about today, and I know it's been linked here, but we don't do this very often, is we're going to talk about a way to talk about solution concentration. So we talked a little bit about terms, talked a little bit about the difference between weak and strong and non-electrolytes, and now we're taking a look at solutions and how we can do this. So this is something that's review for most of you. Okay? So most of you, this is review. So, did I give you guys that? I haven't, have I? So go ahead and write that down, and we'll do one problem before you go. Is found by taking moles divided by liters of solution. So I've got a real easy problem here. Okay? You guys can handle this problem. And this is the problem. You can just plug the numbers in and get your answer. It's just like, you know the formula, you plug it in, you got your answer. So, I guess I made it a little bit more complicated. So, molarity equals moles over liters. So, you guys know how to find moles. Somebody find moles for me. I'm not even going to do it. Somebody calculate moles of NaCl. So what would it be?
Is that
This is 58.45.
I got 0.769.
Okay, 7698.
Yeah, so.
So 0.770. 0.770. Okay, and then the volume, how much is the volume in liters? So how much do we have in liters? So we got 250 milliliters, and you say for every 1,000, I've got 1 liter, so that would be 0.250 liters. So we divide it by 0.250 liters, and it gives us a concentration that would be moles per liter or molarity. So what would that be the answer? Would that be? It would be what? 3.1?
Yeah.
Okay. 3.1 molarity. Really easy, right? That's about as easy as you can get. Okay, so if you want to find the molarity of something, you find the moles of the solute, which is the NaCl. You find the volume of the whole solution, which has to be in liters. You do it, and that's a 3 molarity. And that would be the concentration of sodium chloride. Okay? Really easy idea. Now, this one I'm giving you the molarity, and this is a dissociation. We're taking CaCl2, and we're breaking it apart into Ca and chlorine. So when it dissociates, it goes from a solid into 2 ions that are in aqueous form. So can somebody tell me, based upon what our discussion already, we really don't even have to do a problem on this, but we are a setup on this. If I have 0.35 molarity of this solution, I guess this should be aqueous, but if I have 0.35 molarity of that solution, what's the molarity of calcium ions? And then you still use the ratios. So what would it be? 0.35 molarity. Because it's a 1-to-1 ratio. So what would be the molarity of chlorine ions?
It would be
0.7 molarity, right?
Yeah.
So it's just that ratio thing. So the calcium ions, we would have 0.35 molarity, and the concentration of chlorine ions, we'd have 0.70 molarity. And so because it doubles, because CaCl2, when it breaks apart, it doubles its chlorines for every 1 calcium chloride. It's kind of like an Oreo cookie, right? Break it apart, you got 2 cookies, 1 center. That'd be the same. Calcium would be like your center, and your chlorines would be like your, so if you break apart 10 of them, you got 20 cookies and then 10 centers. So it would be the same. Last one is that this would be like doing it all at once. Those 2 steps all at once. Okay? So I'm going to give you the molar mass of Na2S. And before you go, I'd like you to figure out those 2 answers for the Na2S and the S minus 2. So I'm going to go ahead and give you the molar mass of Na2S. It's 78.03. Okay, so let's do that. That'll be your last thing you need to do. Okay, so here's the answer. You take 20 divided by 78, you get 0.256 moles. You take the 0.256 moles divided by 0.2, and that gives you a 1.28 molarity, capital M is molarity, or you could write 1.28 moles per liter, same thing, and that's the concentration of Na2S. If you want to find the concentration of Na or S molecules, you would have to know how it breaks apart, You get 2 sodium ions for every 1 sulfur ion. So you have 1.28 molarity of the S minus 2. Can anybody tell me what the concentration would be of sodium ions? Yeah, 2.6. So it would be 2.6 rounded up. So sodium ions would be 2.6 molarity. That's it. Okay. So went through a lot today. If you guys get a chance, you can read through sections 4.3. We didn't hit everything in section 4.3 because they have some things on dilution we can hit tomorrow. Okay? And then after that, we look at reactions. Okay?